All right, so that then takes us to the end of module 6. So we've looked at electromagnetism, we've looked at motors, transformers, torque, uh, yeah, like I think that's basically it that we need to cover in module 6. So yeah, general overview of module 6, kind of the stuff that you might need to know in terms of like general points that you might need to know or touch up on for module 6. We can now move on to module 7. So disclaimer is module 7 is very content heavy. So compared to module 6 at least, we'll get to module 8 later on, right? Or you find out later on in the year that module 8 is way more content heavy than all of the modules. But so far, module 7 out of everything that we've encountered will be the most content heavy. So going through module 7 then, we'll first look at the historical methods for calculating the speed of light. So we have Galileo first of all. So what did Galileo do? He basically he just took like him and some other dude. Let's say person A and person B, right? Person A climbed up to mountain A, and person B climbed up to mountain B. That was approximately, I don't know, like 1 to 2 to 3 kilometers away from mountain A, right? So person A now had a timer and a lamp. Person B had a timer and a lamp as well. Person B only had a lamp. Sorry. So what person A did was person A turned on his lamp and timer at the same time, right? And he waited until the light ray traveled all the way to person B on top of mountain B. And then once person B saw the light turn on, he himself would also turn on his lamp. And so then person A could also see the light turn on. So once person A saw person B's lamp turn on, that means that light would have traveled from his lamp all the way to person B, and then light would have traveled from person B's lamp all the way to person A. And so then he would stop the timer, and so assuming that the mountain was 3 kilometers distance, he would technically find the time taken for light to travel 6 kilometers, right? Because light would travel from person A to person B, and then from person B to person A. There's one issue with that, or two issues with that though. First of all, if you look at the speed of light, right, the speed of light is massive, or not massive. It's a very very large value, and so the time, well, in fact, it can travel around the Earth 7 times in 1 second, and so the time it would take to travel 6 kilometers in this case will be very very little. And it's not like Galileo could stand like 40, 50 kilometers away, because then he wouldn't be able to see the other person because of Earth's rotation or Earth's like curvature, right? And so the time was very, very insignificant. And then you have to take into consideration human reaction time, right? Because person B had to see the light turn on from person A and then turn on his own light for person A to record the time, right? And so the time taken for person B to turn on his lamp would be so much higher than the time taken for light to travel between the two mountains. And so there would be a very, very large percentage error. And you can see that because Galileo kind of ended up saying that light would be, I don't know, like around 10 times the speed of sound. So that's kind of what Galileo got. It was very inaccurate, but it was kind of at his time the only way of solving this or like calculating the speed of light in this case. And then we have All-Romer. So what All-Romer did was he used the revolution speed of Io. So he found that the revolution speed of Io changed during different times of year due to differing distances between Earth and Jupiter. And by doing that, he was able to calculate the speed of light. And he said it was around 2.1 times 10 to the power of 8 meters per second. So he used differing revolutionary speeds of Jupiter's moon Io. And his one was a lot more accurate than Galileo. And then we have James Bradley. So James Bradley, he observed stellar aberration, which is basically the changing positions of stars in the sky. Using this, he was able to get pretty close. So he was able to get what we use as speed of sound, speed of light right now. He got 3 times 10 to the power of 8 meters per second, like around there. So that was very accurate, right? So we've significantly increased in accuracy moving up now. So after James Bradley now, we have Hippolyte Fizeau, right? He used the rotating tooth wheel contraption that you can see a diagram that I've drawn off, right? So he's using the rotating tooth wheel contraption. He's shown light through a gap, which is reflected back by a mirror very far away. So the light would shine through a gap in these cogwheels, right? And it would be reflected from a mirror very far away, coming back, right? And he changed the speed of rotation until the reflected light couldn't be seen. What does that mean? Well, it means that after the light having traveled twice that far distance, it would travel past the cogwheel to this mirror really far away. As it was coming back, the cogwheel would have moved enough so that instead of light passing through a gap now, it would pass through the adjacent cogwheel. So initially, light would pass through a gap between the cogs, right? And so he would turn it enough, so he would turn the wheel fast enough so that when light came back, it would hit this cog adjacent to it, and therefore light would be blocked out. So he would increase the rotational speed and keep increasing it until the reflected light ray couldn't be seen. And that's the method that he kind of used. And using this method, he was able to get around 3.1 times 10 to the power of 8 meters per second. So very accurate as well. Then we have Foucault, right? So Foucault, he used a rotating mirror contraption where he reflected light to a stationary mirror so that by the time the reflected light came back, the mirror would have rotated and the angle between the light source and the reflected angle would be measured to calculate C. So if you look at this, right, so you have a light source, it gets reflected to a stationary mirror. As it's being reflected to the stationary mirror and coming back, the rotating mirror will have rotated a very tiny bit, and that will cause this reflected light ray to be like deflected a little bit, right? And so we'd be seeing that deflected light ray, and by knowing this angle or the deflection angle, we'd be able to calculate the speed of light. So what's important here is you guys need to know at least, I would recommend knowing around 3 to 4 very detailed historical methods for calculating the speed of light, because it's a very high possibility that they will be tested, right? Either in your school or in the HSC or in trials. So I'd recommend knowing Fitzo, knowing how to draw this diagram. Always draw diagrams, by the way, whenever you come to like 4 or 5, even like maybe not 3 mark questions, but even in some cases 3 mark questions, I would recommend drawing diagrams, right? But definitely for these types of like method questions, right, always draw diagrams. So if you're talking about Fitzo, always draw a diagram. Even Galileo, just draw like 2 mountains and 2 stick figures standing on top of the 2 mountains. It really helps boost your responses. So like have a diagram or like have a sample diagram that you draw back on when you look at Fitzo and Foucault's experiment. It's kind of hard to do that with All-Romer and Bradley. But yeah, I'd recommend knowing Fitzo. I'd recommend knowing Foucault. The other 3, right? Galileo, very simple. So you can always have Galileo in the back of your mind. If you forget one thing, it's like a backup. And then you can pick between All-Romer and James Bradley, whichever one you want to look at next. So yeah, those are the historical methods for calculating the speed of light. With that now, we can move on to the electromagnetic spectrum and question, what is light? So we know light is an electromagnetic wave, but then what exactly is an electromagnetic wave? Well, an electromagnetic wave is a wave consisting of electric and magnetic fields oscillating at right angles to each other, which can self-propagate through empty space. So the important things in this case is that an electromagnetic wave consists of both electric and magnetic fields, and these electric and magnetic fields oscillate at right angles to one another, and they can self-propagate through empty space. So they don't need a medium, and they can propagate themselves. So let's unpack what we mean by self-propagate. So I briefly brought this up when we were looking at module 6, but we'll look at it in more detail now. So Maxwell's 4 equations, So he basically said that a point charge produces an electric field, that's Gauss's law. An accelerating point charge produces a changing electric field, also Gauss's law. And a changing electric field produces a changing magnetic field. A changing magnetic field produces a changing electric field. And these last 2 steps repeat one on one. So a changing magnetic field will produce a changing magnetic field, which will then produce a changing electric field, which will then produce a changing magnetic field, so on and so on and so on. And that is what we mean by self-propagation. So if you look at this now, an accelerating point charge produces a changing electric field, right, via Gauss's law. That would mean that if an electron is accelerating, it will produce a changing electric field, which will produce a changing magnetic field, which will change a changing electric field, etc., etc., etc. So that would indicate that accelerating point charges will emit electromagnetic radiation. Keep that in mind, because that might be That info might not be very useful now, but it definitely will be useful in Module 8. Accelerating charges via Maxwell's 4 equations produce EM radiation. In terms of these laws, you won't need to know any equations. There are equations for these laws, but you won't need to know any equations. It's also unlikely that they'll specify Ampere's law and Faraday's law. Just know his 4 equations. And let's look at where Maxwell comes into play. So basically what he did was he put together the 4 equations to unify electricity and magnetism for the first time. So basically he predicted the existence of EM waves. He rearranged the equations to predict that EM waves should travel at a speed given by this, right? And because this constant speed was very similar to, at the current time, the known values for the speed of light, he predicted that light was an EM wave as well. He wasn't able to verify anything. He wasn't able to he was able to mathematically suggest, but he wasn't able to experimentally verify anything. So he was able to predict the existence of EM waves, and he predicted that EM waves should travel at that speed, and then he predicted that light was an EM wave. So, yeah. He also described electromagnetic waves as self-propagating waves with electric and magnetic fields oscillating at right angles to one another. Alright, so why is this all important then? Well, his proposal 1 is that light is an electromagnetic wave, as I mentioned before, and his proposal 2 is light is a self-sustaining mutual generation of magnetic and electric fields, and hence electromagnetic. So the implication of this is that light is just one part of the entire electromagnetic spectrum. We know now that the EM spectrum has like X-rays, gamma rays, microwaves, infrared radiation, ultraviolet, and like a whole bunch of things, right? So we know now that light is just one part of the entire electromagnetic spectrum, but Maxwell's proposals led to this implication, that light is simply one part of the entire EM spectrum. All right,